So today we begin a new chapter in refrigeration, and I'll focus on refrigeration first, and later we'll talk about heat pumps as it's a simple, different perspective on refrigeration, what a heat pump system is. And we'll start by a review of Carnot refrigeration, and then get into vapor compression refrigeration, the most common type of refrigeration that you find in your homes, in air conditioning systems, in refrigerators, freezers, that's out there in practice, vapor compression. So Carnot is the benchmark. It's the gold standard. It's how we first analyze the refrigeration, and then we see how that's impractical. It's not any Carnot refrigeration systems out there in practice, but that it's we see it does set the standard, and then we modify it, and then we have our actual vapor compression refrigeration system. So when we have refrigeration, we're going to talk a little bit later about refrigerants, but refrigerants are things like R22. I know that's being phased out. R134A. How many people know what's in their home split system? What do you have in your home? 134A? All right. Anybody else? There's a 404, 410, and some other refrigerants out there in practice. There's really a lot of refrigerants, but you just need to learn how to work with one or two and then analyze it. So then you have how many components? Well, we're going to have a compressor. And the refrigerant's going to come into the compressor at low P, low pressure, and go out at high P, high pressure. Now, what is the goal of a compressor? To boost the pressure, to change the pressure. Okay. In the result, as you change the pressure, a lot of times, if it's a vapor, you're doing a lot of work. There's a lot of reduction of volume. Hence, the temperature goes up a lot. Hence, the enthalpy it goes up a lot. Hence, it's very expensive to compress or run a compressor compared to running a pump, a water pump. When you put fluid through a water pump, it's incompressible. There's very little, there's a great change in pressure, but very little change in temperature, very little change in enthalpy. Compressor, great change in volume, great change in enthalpy, great change in temperature. So maybe we come in at state 1 and we go out at state 2. And then you put it into a condenser. A condenser. Okay, well, what's the purpose of a condenser? You're going to transfer some heat out of that working fluid and condense it. What do you think comes out of a condenser? What is the state of the fluid that might come out of the condenser? Liquid. Liquid. So maybe it comes out at state 3 as saturated liquid. All right, now for the Carnot, you're going to put it through a device called the turbine. This looks a lot like the Brayton cycle, right? You have a compressor turbine, but guess what? Putting saturated liquid at high pressure into a turbine is very difficult to build a turbine that can actually do that. So this device doesn't exist, but it's a good theory, a good benchmark. So we would have some work coming out of the turbine, just like we have to work going into the compressor. Now, let's continue on. It comes out of the turbine. Tell me a little bit about the pressure at state 4. The same as the pressure at state 3? No. Pressure at state 4, the outlet pressure of the turbine, high or low compared to the pressure? It's a lot lower. And actually, we have negligible pressure drop through the condenser, and so pressure at 2 is equal to pressure at 3. And then the last device is the evaporator. And the pressure going into the evaporator is pressure 4 is the same as the pressure going out of the evaporator, pressure at 1. So we have really only 2 distinct pressures. You have the high side pressure and the low side pressure. The high pressure is equal to P2 is equal to P3. whatever pressure it is, and the low side pressure is P1 equal to P4. Two distinct pressures, that's it. Okay. Now, let's talk a little bit more about this. What's really unique about the Carnot refrigeration system is that not only is state 3 saturated liquid, but state 2 is saturated vapor. How did they achieve that? Well, we'll talk about it a little bit, but basically it's picked to be saturated vapor. Because if you have constant pressure in the condenser, even though you're rejecting heat, even though the heat is going out of the fluid, right? QC is out of the working fluid flowing through the condenser. The pressure of the fluid does not change. P2 is equal to P3. Does the temperature of the fluid change? T2 to T3. Is the temperature 2 equal to the temperature 3? It is, and it's the saturation temperature. So it's T3 is equal to T2, and that's equal to the saturation temperature at the pressure. I'm running out of room. Maybe get rid of this up here. Sorry about that. T2 is equal to T3 is equal to the saturation temperature at that high pressure, P2 or P3, and that's our high temperature, TH. So you reject heat at high temperature. Likewise, if you're in the evaporator, guess what? The temperature at 1 is equal to the temperature at 4 is equal to the saturation temperature at the low pressure, let's call it P1, and that's the low temperature, TL. Which temperature is greater? TH is greater. You're pumping heat uphill. You're pulling in heat from something that's cold, Q evap, pulling in heat from something that's cold, and dumping heat, more heat actually, at the high temperature. That's the difficulty of vapor compression refrigeration or Carnot refrigeration system or any refrigeration system, is pumping heat up the temperature scale. All right. The refrigerant flows through each of these devices. What you're going to do is a first law analysis for each device. So you have to be able to write down first law to get the specific work into the compressor, meaning the work in kilojoules per kilogram of refrigerant flowing through the condenser. Isn't that equal to H2 minus H1 after I do a first law analysis? Hopefully you're getting very good at that. How about QC? QC, it comes in at high temperature, high enthalpy, and goes out at much lower, H2 minus H3. That's a first law analysis around that condenser. How about the work out of the turbine? It's going to be H3 minus H4. And the heat transfer per unit mass, specific heat transfer in the evaporator is H1 minus H4. Make sure you understand each one of those, okay? How you get it, first law analysis around each of those components. Steady state, neglect changes in kinetic and potential energy, and sometimes, well, for each component, it's either a work transfer or a heat transfer, not both. All right. So, how would I understand the components, I understand the flow, the refrigerants, I understand the pressures. Maybe how do I calculate those enthalpies? I like to encourage students to make a table of the states. State 1, State 2, State 3, State 4. And then think about how I'm going to be able to fix each of those states. And then once I've fixed the state, then I get other pressures and temperatures and properties like entropy and enthalpy. And so think of making a pressure. Maybe I put it in kilopascal. Maybe temperature, degrees C. Maybe quality. Maybe enthalpy in kilojoules per kilogram. Maybe entropy in kilojoules per kilogram Kelvin. Yes, I know I've solved a few problems before, and I like this arrangement. I know these are the properties of interest. I could put in specific volume. I could put in internal energy. I could put in flow exergy, but they're not essential. H's and S's and quality are really the key parameters, in addition to pressure and temperature. Okay. So, state 2 is a key one right here. we said it's at high pressure and it's saturated vapor. So I could say, knowing pressure and maybe that the quality at 2 is 1. Isn't that saying the same thing? Quality is 100%, hence it's saturated vapor? Yeah. So knowing the pressure at 2, the high pressure, and the quality at 1, I can go out and I can get the temperature at 2. How would I get it? It's the saturation temperature at that high pressure. How would I get the enthalpy? It's H of G. How would I get the entropy? S of G. True? Out of the table, or using a software to evaluate properties. How about state 3? If I look at state 3, oh, it's saturated liquid. So it's the pressure and the quality, but the quality is 0. It's the same high pressure, isn't it? Aren't these the same pressures? Now, knowing that, 2 independent intensive properties fix the state, I go get the other properties. I get T2. T3. Is T3 the same as T2? Are they the same temperature? They are, and it's the high temperature. It's the high temperature. Okay. And then I get H of F and S of F. True? Okay. Now, how about these other properties? Well, sometimes a diagram helps us. Let me put in here a temperature entropy diagram. There's the dome. True? Put on a line of constant pressure. What does a line of constant pressure look like? Something that comes up, scoots across, and then goes up. That one's the low pressure. This is the low pressure. Put a line of a different pressure, it's the high pressure. Pressure high. Do those 2 lines of constant pressure look okay? Where is state 2 located? It's at the high pressure saturated vapor. Yeah, that's right. It's at this corner right here. Isn't that state 2? Where is state 3? Saturated liquid at that high pressure. Once you got those 2 states, visually, where is state 1 and state 4? Right below 2 and 3. So you just follow right below, straight below. Now this is state 4 and this is state 1. So on a temperature entropy diagram, TS diagram, Carnot refrigeration is tucked under the dome, and it's a rectangle. It's a rectangle. Okay. Notice what happens between 2 and 3. Well, that's it's in the condenser. It's condensing. What's happening between 4 and 1? Well, it's in the evaporator. It comes in at a low quality. X4 is maybe 20% or 25%, and it goes out 80 or 90% at X1. The quality at 1. That's 80 or 90%. Okay, so this really helps us figure out, do we know the pressure? The pressure low and the pressure low. So those 2 pieces of information help me fix the state. But what other information helps me fix state 1? What property? S. That's right, S. S is known. How do I know S? Well, S1 is equal to S2. It's like I've got to calculate state 2 first. And then I can back up and get state 1. And then S4 is equal to S3. So I get state 3 fixed, and now I can go and get state 4 fixed. Okay, determinant. So I then am able to go and look up T4 and T1. What's the difference between the low temperature T1 and the low temperature T4? Are they the same temperature? They're the same temperature. And then I look up and I get H4. How do I get I'm sorry, this is H1 right here. How do I get H1? I use S and the pressure. I'll first get the quality of state 1 as an intermediate step. How would I get quality of 1? That's S1 minus S of F at 1 divided by S of G at 1 minus S of F at 1. True? So I go to that low pressure, and I get the saturated liquids entropy, the saturated vapors entropy, and then S1 is between the two, and it's a mass fraction quality to calculate. That's how I get X1. True? Likewise, once I get X1, then H1 is equal to H of F1 plus the quality 1 times HFG of 1. True? Good. So that's how we get the quality. Likewise, the same thing, you get the quality at 4 and the enthalpy at 4. Once I have those, then I can finish the calculation. Let me do this for, I want to make some room here, so I'm going to take this stuff and I'm going to just squish it in the box and get it over here. Okay. Maybe I'll put it over here, get it out of the way. Because what I want to do now is I want to compute some parameters of importance. I can compute something like what is the net, specific net work into the system. That's a lowercase w, net. And that net work is into the system. Okay? Well, it's the work per unit mass into the compressor minus the work per unit mass that the turbine develops, because that's a contribution out. So this is the net work into the system. True? Okay. Can I calculate Q net? And I probably want to calculate Q net out of the system. Well, isn't Q sub C out in the condenser minus Q sub E into the evaporator? All right? So if somebody's asked me, well, calculate the net power that needs to be provided to the system, wouldn't it be the product of the mass flow rate times the specific net in? And if somebody said calculate Q dot net out of the system, that's going to be mass flow rate times Q net out. True? So I could do it on a per unit mass basis, specific power or specific work. Likewise, net power, net work. Okay, now, are these two equal in magnitude? They better be, right? And are these two equal in magnitude? Sure, they're equal in magnitude. Okay, so we could calculate the net power required to drive the compressor. To drive the Carnot refrigeration cycle. There's another thing of importance or interest, and that is the coefficient of performance. COP for coefficient of performance, and we put a subscript R for refrigeration system. I know this textbook uses a Greek symbol like gamma. Why do we need new Greek symbols? Let's just do COP, okay? I'm deviating from the textbook here, all right? I recommend COP for coefficient of performance. If you want to use gamma, go for it. So I understand gamma too. All right, but if you don't want to tuck gamma into your mind and say, oh, in this class, gamma means this, right? How many classes, if you go back, let's see, in solids, what does gamma stand for? Heat transfer, what does gamma stand for? You know, dynamics, what does, oh boy, right? Okay, now, coefficient of performance typically is a ratio of what you want over what you had to provide or pay for, what it costs to drive the system. Okay, so what do you want in a refrigeration system? Now, let me say there's 4 potential answers. For what you want, do you want a large WC? Do you want a large QC? Do you want a large WT? Or do you want a large QE? Do you want a large amount of work to provide to the compressor? A large amount of heat rejected in the condenser, a large turbine power out, or a large heat transfer into the working fluid in the evaporator? What do you want from a refrigeration system? In the evaporator. All right. Now, you have to pay something to make the system work. in perspective of work, what work did you have to make to provide? You had to provide W net N. That's your good definition for the coefficient of performance of a refrigeration system. Right? So there's a COP. Now, somebody says, you know what? Why can't I compute Q sub E and divide it by Q net out? Will that also work, Professor? What do you think? Yeah, it will. Can I replace Q net out by QC minus QE? All right. Let's continue that line of thought. Could I replace that by 1 over QC divided by QE minus 1? Algebra. And then I go back, all the way back to chapter 5 when it introduced entropy in the second law. And there was somebody's inequality, bonus points. Who can remember? Whose inequality was it? That was a foundation for the introduction of the new property called entropy. Clausius's. So what he said was, when you have a system that's completely reversible, you can replace the ratio of Q's by a ratio of T's. T's. Well, we're studying Carnot. We can do that now. Okay? So all of the QC, all of the heat transfer out in the condenser happened at what temperature? TH, the high temperature. So this gets to be 1 over TH divided by, and all of the heat transfer in the evaporator, it all happened at one temperature, TL, the low temperature, TL. I know I didn't leave enough room, and it looks messy. Let me try and tuck it down here, bring this down here now. So the coefficient of performance, refrigeration, Carnot, can be written as TL over TH minus TL. Have you seen something like that before? Sure. Yeah. Okay. Okay, but Professor, could I actually compute these H's, then go and compute all the Q's and the W's, and then compute the COP this way, and would it still give me the same answer? It doesn't look like it would, but guess what? It does. It does. Okay? It does. All right. Let's go ahead and move to a problem, huh? Refrigerant 22. I know it's being phased out, but we have a table for R22 in our textbook, as well as it's in a lot of computer programs to evaluate thermodynamic properties. It's a common refrigerant. It's a working fluid in a Carnot vapor refrigeration cycle. Now, Carnot means it doesn't exist in practice, but it's a theoretical refrigeration cycle. Carnot, benchmark, gold, all reversible. The evaporator temperature is 2 degrees C. The saturated vapor enters the condenser at 52, and saturated liquid exits the condenser at the same temperature of 52 degrees C. The mass flow rate is given to be 5 kilograms per minute. So probably from memory you want to go ahead and sketch the major components. Condenser, this is our turbine, this is our evaporator, this is our compressor, flow like this, like this, like this, like this. And we have now a mass flow rate given for this problem, m dot. And that's flow, the rate at which it flows through each of those components, a steady state flow. Yes, sir?
Yes, sir. How do I assume that's a turbine and not an expansion valve?
We're going to replace it. Because the Carnot is not practical, you can't get a turbine like that. So what do? You try to get the functionality of what the turbine's doing, and it's a pressure letdown or a pressure drop across it. You put a valve there to replace it. But that's the next thing we study. So we'll study the Carnot, and then we'll go to
so
the.
I don't assume because it's not really telling you to read it both ways.
Yep. Well, when you have this key word in the problem statement, that means you put a turbine in there that doesn't exist in practice. It's the turbine that ingests saturated liquid. Good luck. All right? All right. And then you want to go ahead and make a property diagram, refresh your memory. We have a temperature entropy. Go ahead and put on a low pressure, put on a high pressure lines, P low, P high. Put our states, help us. That's state 1, state 2, state 3, state 4. Okay. It's a nice rectangle tucked under the dome on a temperature entropy diagram. And now they ask us to calculate the rate of heat transfer to the refrigerant passing through the evaporator in kilowatts. Well, what are we asked? We're asked to calculate Q dot in the evaporator. Is that the mass flow rate times lowercase q evap? And is lowercase q evap equal to H? Let me put the states in here. 1, 2, 3, 4. Is it H 1 minus H 4? Is that what it is? Yeah, that's what it is. So I need to get the H's. I've got the M dot. And then I can get the answer to the first question. So guess what? I put a table together. So I put a table of, let me do it just my standard way. State number, 1, 2, 3, 4. Then I'm going to have the pressure. I'll talk kilopascal. Temperature, degrees C, or Kelvin, add 273, right? If you look at this, that low temperature is 2 degrees C. 273 Kelvin plus 2 is 275 Kelvin. All right. The next high temperature is 52. 52 degrees C plus 273, 325 Kelvin. So you had to pump the heat uphill, so to speak, on a temperature scale by 50 Kelvin. That's the change, up, right? Is that equal to a 50 degrees C up? Yes, it is. It's the same magnitude of temperature increase that you pumped it from one quote-unquote reservoir and dumped it to another reservoir. All right.
The delta would be different.
I'm sorry?
You just can't use C degrees Celsius because the delta would be
The delta T is 50 Kelvin, which is 50 degrees C. Delta. But when it's subtraction or addition. But when we get to the using the formula for COP, put TL and TH in absolute temperatures. Yep. So what it is they told us this temperature is 2, and this temperature is 2, and this temperature is 52. Whoops, can't write. 52, and this temperature is 52. True? Well, the saturation pressure for 2 degrees is 531 kilopascal for R22. So this low pressure is 531 kilopascal. How about the high pressure? Oh, it's around 2,000 kilopascal. So right here, this line, put it at around 531 kPa, and this line around 2,033 kPa, and there you go. Okay? All right. We had the quality. We had, it's going to be 1 and 0. We had the entropy, enthalpy. Just look up H of G, 417.65, and H of F, 266.22 kilojoules per kilogram. And this S, kilojoules per kilogram Kelvin, will be 1.6827 and 1.2170. Notice, I did not use the values in our textbook. I used off of 2 software programs. Okay, RefProp, that's one of them, RefProp, I mentioned before, and the other one from the University of Alabama. Okay, and they give consistent values. Why are the values for S and H different than in our textbook? Because in our textbook they used a different reference state for the data for refrigerant 22. Everything's shifted. Everything's shifted. Okay? All right. But once you're in the one system, just use the table in the textbook completely for the whole problem. Don't jump back and forth between them. or use the software total. You know, don't jump back and forth for the properties of this refrigerant. All right. So this entropy is 1.6827, and this entropy is 1.2170. We're able to calculate the quality. Quality is 0.912, and likewise 0.282. Then we calculate the enthalpies, 387.87 and 259.75. All right. So then I'm able to calculate the Q in the evaporator, 128.12 kilojoules per kilogram, multiplied by m dot, which is in kilograms per minute, but a minute is 60 seconds, true? And you calculate that Q dot in the evaporator is 640.62 kilojoules per minute, or it's 10.68 kilowatts. All right? Okay. For part B, calculate the rate of the heat transfer to the refrigerant passing through the evaporator in tons of refrigeration. It's the same answer as part A, just in specific units. When you talk about refrigeration, you often talk about the capacity or the rate of cooling it can provide, and they report it in tons of refrigeration. So 1 ton of refrigeration, or tons, ton or tons, or RTs or TRs, okay? Just try TONS, okay, for abbreviation for tons of refrigeration. It's 211 kilojoules per minute. So you use that conversion factor and you calculate Q dot E, the same thing, but we're reporting it now in tons of refrigeration, 3.04 TONS. All right. Part C is the net power input to the cycle. Well, the net power in kilowatts, that's net in, was the mass flow rate times lowercase specific net. True? We did that, and that's the difference between the compressor in minus the turbine out. Let me jump to the answer. The net in is 1.94 kilowatts. And then for part D, what is that coefficient of performance? Is the coefficient of performance of refrigeration, is it going to be, hey, I was able to get 10.68 kilowatts of cooling in the evaporator by providing 1.94 kilowatts of power to the system, giving me a COP of refrigeration of 5.50? Hey, that's greater than 1. Yep, you should be able to get a coefficient of performance greater than 1. Unless you have some severe temperature. And the further you have to open it up, that delta T, it's harder for the system to achieve your coefficient of performance. It's going to degrade. But this is Carnot. This is very good. Let's take a look at this. Somebody says, how does this 5.50 compare with TL over TH minus TL? Well, there's our two temperatures. If you plug them in, good to 3 digits. I didn't check to 4 or more. It's 5.50. All right? Any comments or questions about this problem? Now we come to the practical. Can I purchase a turbine like that? No. So the engineer a long time ago said, theory is great, but I need something that's going to work in practice. So I need to replace it with a device which achieves the pressure drop. I'm not going to be able to get work out. I'm going to have a very simple device. It's an expansion valve. So when you go to a practical Carnot, a vapor compression refrigeration system, you replace it by an expansion valve after the condenser. All right? And then this is the evaporator. Do we still want to feed at state 3? Do we still want to feed it saturated liquid? coming out of the condenser. If the condenser really does a good job of condensing, and as engineers, you say, yeah, we should be able to build a pretty decent condenser. Guess what's going to come out? Saturated liquid. Okay? Now, the other thing which was a little impractical was this compressor. Let's go take a look again. What was going into the compressor at state 1? 91% quality, two-phase liquid vapor mixture. Compressors don't like any liquids at all going into them. Okay? So, you say to yourself, what's going to go into the compressor? It's not going to magically come out with saturated vapor. What's going to go into it is saturated vapor. So that's our big change. Right here, this is the area of big change from the Carnot. It's saturated vapor going into the compressor, not out. The next big change, there's no turbine. It's just a restriction. It's just a valve. Okay, so we still have the same numbering system. This is number state 2. This is state 4. Let's go ahead and see if we can sketch this on a temperature entropy diagram. Put the dome, put our line of low pressure, put our line of high pressure. The high pressure, let me do this. The low pressure is the pressure in the evaporator. The high pressure is the pressure in the condenser. There's still just the high pressure side, low pressure side. Okay. Can you fix state 1 on this diagram? Is this where state 1 is? Saturated vapor, low pressure? All right, good. We still have a really great compressor. Isentropic. Reversible, no heat transfer, it's isentropic compressor. Where is state 2 on this diagram? Straight up. All right, so if we go up here, guess what the temperature is at state 2 compared to the temperature of state 3 coming out? Isn't this 3? Look at that. So right away, when you start to go into the condenser, you're going to have to first cool it down before you can start condensing. It's coming in superheated vapor, and it needs to be cooled until it becomes saturated vapor, at which point then it can start to condense. All right. Right away, we've just broken the rule about all of our heat transfers at high temperature TH, and all of our low heat transfers all at TL. It's not at all at TH anymore. The Carnot equation isn't going to work. Carnot efficiency equation is not going to work. Now the other one is, what about going through this expansion valve? If I do a first law analysis around this expansion valve, I conclude that H4 is equal to H3. True or false? If I do a second law analysis, S4 is equal to S3 plus sigma. Is there any sigma, any irreversibilities in the expansion valve? There's no work in, there's no work out. It's just kind of, I know we analyze simple components to death in Thermo 1, but you got to do that so that when you put them into the system, you know how they behave. What are some sources of irreversibility? Okay, how about heat transfer through a finite temperature difference? Bad. All right, larger the temperature difference, the more irreversible the heat transfer. How about two streams of different mixing components and they mix? Let's say I take a stream of oxygen, pure oxygen, stream of pure nitrogen, I mix them. Can I turn that around and just have them separate willy-nilly? No, it's highly irreversible. How about friction? Right? Well, in fluid flow, friction is fluid flow through a severe pressure drop. This is big-time fluid flow friction through that expansion valve. Guess what sigma is? Big. There's no way to have an reversible expansion valve. It's by nature. It's just, that's what it is. It's friction, okay? So this S4 is greater than S3. All right. So where do I find state 4 on the TS diagram? Do I find it straight below state 3? Do I find it a little to the left or a little to the right of state 3? To the right. To the right, right? So, now the other thing is when I draw, whoops, just erased my dome. When I draw my line, do I want to draw a dashed line or a solid line from state 3 to state 4? I want to draw a dashed line. Why, Professor, do we draw dashed lines? Sometimes, and solid lines other times. I don't understand this. Because that's the convention used in engineering thermodynamics. If it's a solid line, it indicates reversible. If it's dashed, no, not reversible. Right? True? That path, that process going from state 3 to state 4, going through that expansion valve, this is my expansion valve, is highly irreversible. Put a dashed line. So there you go. There's our temperature entropy diagram. Do you think we can get equations for each of the major components? What about the work to drive the compressor? Would that be H2 minus H1? Sure. How about the heat transfer out of the condenser? Maybe I should draw the directions of these. This is Q out the condenser. How about Q into the evaporator? All right, is that going to be H2 minus H3? Sure. And then Q in the evaporator, is that going to be H1 minus H4? I don't have another work. There's just now one work with two Qs. Can I talk about the coefficient of performance for the refrigeration system, the vapor compression? Yes. So what would it be? It would be what I desire divided by what it costs to run. And I can express those in terms of enthalpies. I'll need to get a table of my states. State 1, State 2, State 3, State 4. Pressures, temperatures, quality, enthalpy, entropy. And maybe the first one is going to be my low pressure and it's saturated vapor. So pressure and quality of 1 for state 1. Fix this state 1. How about going through the compressor? How about the high pressure and entropy? Pressure and entropy. S2 is equal to S1. How about for state 3? It's going to be pressure and saturated liquid. So pressure, quality 0. And then state 4, low pressure, enthalpy, low pressure, and H. Why? H4 is equal to H3. You bring it down. All right. Well, I'm out of time. I would put data to this, but I think if you understood that, you're a long way in solving these problems. I have your exams. I'll spread them out on the table up here.